Hi everybody, welcome back to the section 2.6 video. In this video, we're going to take a look at an example applying Euler's method to solve a differential equation. So let's look at example 1. Consider the initial value problem, y prime equals x plus y squared, and an initial condition of 0, 0. So it's saying use Euler's method to obtain an approximation for y of 0.2. So when we have an x of 0.2, we want to get the output for that. And we're going to use the step sizes of 0.1 first and then 0.05 second. So let's just rewrite what the formula for Euler's method is. It is the next yn plus 1 equals the current y sub n plus h, our step size, times our function of x and y. So that's the method we're going to use to obtain an approximation. So this is note a couple things that uh, what is f of x and y? Well, that's for our differential equation, what our function is. So here we'll say like note f of x and y is the equation x plus y squared. Okay, that's our function of x and y as it pertains to our differential equation. And, we're going to be going through approximations and step sizes and increments. So our first point is our initial condition. So this would be x naught and y naught. So 0, 0, it's the point, 0, 0, x naught, y naught. That's what we're going to be starting out with when we go through our iteration. Okay, so it's talking about going through a step size of 0.1 first. So let's try that out. So for the step size, h equals 0.1, what our setup would be is y sub n plus 1 equals y sub n plus 0.1, our step size, times our function. And we're going to write this in terms of xn and yn. So x plus y squared turned into x sub n plus y sub n squared. Okay, so we're going to use this and we're going to go up each step size. So we're starting out at x equals 0. So our next approximation is going to be adding our step size to x naught. So our step size is 0.1. So our next approximation would be, 0 plus 0.1, so 0.1. So we won't say this all the time, just trying to give us a better idea of how this works, but our next approximation would be y1. Okay, that's what we're calculating. But what that is approximately y of 0.1. Okay, that's the y value I'm trying to find in my next approximation. And that's just me plugging in what I have already. So it would be 0 plus 0.1 times 0 plus 0 squared. And where am I getting these numbers from? Well, this is y naught, this is x naught, and this is also y naught. Okay, so I'm using my current values to get my next value. That's what iteration is. Okay, so when we calculate all this, it's just all going to go to 0. So this equals 0. And so my first point using approximation is 0.1 comma 0. And remember, this is my x1, this is my y1. Okay, so we want to get up to zero point 0.2 for x. So let's do another approximation. So y2 is going to be y of zero point 0.2. I'm adding zero point 0.1 to zero point 0.1. I'm going up a step. So this would be 0 plus zero point 0.1 times zero point 0.1 plus 0 squared. Where am I getting these numbers from? Well, now it's my current a approximation, which is y1, x1, and y1. And I'm using this to obtain my y2. And, we could backtrack a little bit, like this is x1 and this is x2. Okay, so if we calculate all these, what I get is 0.01. And so I have the point, 0.2, and 0.01. And that's pretty much my answer. I wanted to get to y of 0.2, and we found that to be 0.01, and that's my solution. So x2, y2. Okay, so that is pretty much the idea of Euler's method. And what I like to do at the end is just give a clean table summary because we're just doing some calculations and uh, not putting everything too cleanly. So I like to do like a end table for your iterations and x sub n and y sub n for all the components that we gathered to give a clean look. So we started out with the initial condition 0, 0, and that's of course when n equals 0. And then we did our first approximation and we got 0 0.1 and 0. And then we did our last approximation for n equals 2, 0 0.2, and 0.01. Okay, so that's how we would do uh, one of these types of step sizes, 0.1. 0.1 is a very generous step size, but let's go ahead and move on to 0.05, that step size, because that one is a bit smaller, and so we're going to need a couple more iterations. Okay, so now for the step size for the step size 0.05. Our setup would be y sub n plus 1 equals y sub n plus now 0.05 times x sub n plus y sub n squared. Okay, we're using the same initial conditions from up above, 0, 0. So to get our next approximation, we need to go up a step size. So our first one is going to be y adding the step size to 0, 0.05, which is approximately y sub 1, and that's going to be 0 plus 0.05 times 0 plus 0 squared. And where am I getting these numbers from? Once again, it's y naught, this is x naught, and y naught. Okay, just using my current values to get my next approximation. That's what iteration is. And so what I get is 0. And so I get the coordinate point 0.05 and 0. Okay, this is my x1, that's my y1. All right, let's try another one. So increase the step size, so 0.05 plus 0.05 is going to be 0.1, I'll say 1.10. And so this is approximately our y2. And when I plug in my values, I get 0 plus 0.05 times 0.05 plus 0 squared. And let me just annotate again what values these are. This is y1, x1. Let me use a different color, in fact. Y1, x1, and y1. And this is x2 that I'm looking at. I could go back and say x1 just to make sure we know what numbers represent each other because we have a lot of repeating numbers. But let's go ahead and calculate this. What this becomes is 0.0025. And so I have the point 0.10, 0.0025. Okay, and that's my x2 and y2. Okay, remember, we still want to get up to y of 0.2. So the 0.05 step size is taking a little longer than our previous step size of zero point 0.1, but we'll get there. So now increase the step size. So 0.01 plus 0.05 is 0.15. So that's going to give us our y3, and that is going to be 0.0025 plus 0.05 times 0.10 plus 0.0025 squared. Okay, and we'll do it again. What numbers are these? Well, this is our y2, x2, and y2. We're using the twos to give us the third approximation. And so when we calculate this, it ends up being 0.0075 now. And so I have the point 0.15, 0.0075, and that's y3, excuse me, x3, and y3. Okay, so still not there yet. We need y of 0.2, but increasing the step size is going to get us there now. So this is approximately y4, and so this would be 0.0075 plus 0.05 times 0.15 plus 0.0075 squared. Okay, so this ends up being 0.0150. And so we obtained our approximation for y of 0.2. Let's just write it out like y 0.2, 0.0150. That's x4, that's y4. Okay, so we got our solution. Y of 0.2 equals 0.0150. Okay, and once again, I like to just put everything in a nice table of our indexes, our x's, and our y's. So we went up to n equals 4, so 0, 0, 0. Our x1, y1, 0.05 and 0. Our x2, y2, 0.10, 0.0025. Our x3, y4, 0.15, 0.0075, And our last one are fours, 0.20 and 0.0150. Okay, so that's how we apply Euler's method to a differential equation. So we're able to solve an initial, or we're able to use initial condition to help us solve a value of zero. In this case, is y is 0.2. But okay, so that's it for this video, and I'll see you in the next one. Okay, take care.